Hello everyone, I am Akhilesh Kumar Srivastav from ABS Engineering College, Ghaziabad. In the series of operating system lectures, we will discuss today about the partitioning schemes. We will see that how the memory can be effectively utilized by the processes. The scheme that we will discuss today is the very basic scheme and it has many of the demerits. We shall look at what are the demerits and will improve it further in the subsequent lectures. So, let us have a look at the background of what we have discussed on the last turn, and then we shall have the study about the logical and the physical addresses today. We will then look at the MMU, which is responsible for the conversion of the logical address to the physical address, and finally, we will discuss about today's main topic, which will be multiprogramming with fixed number of the partitions. So, we have discussed yesterday also that whenever a program has to execute, program has to become an active entity, it is known as the process, and it will be process when it will be brought from the hard disk to the main memory. Here the main memory means the RAM, and if the CPU has to access the instructions, it will refer to the main memory, and main memory instruction reading can be performed in several CPU cycles. However, if the instruction is there in the register, then accessing the register requires only one CPU cycle. Whenever the memory is read, memory is given a series of the addresses for the read operations, and similarly it is given a series of the addresses for the write operations. We usually say that the reading operation from the main memory is not instruction oriented, but it is a block oriented. So, a bunch of the instructions or the bunch of the data is read at the same time or written at the same time. So, hence these multiple CPU cycles are involved in reading or the writing operations. The responsibility of the memory management unit or the memory management part of the operating system is to maintain a balance between the main memory and the cache also, because cache is a faster memory. So, cache memory management is also the part of the memory management functions of the operating system. The cache memory is a semiconductor memory as that of the main memory, but since cache location is usually near to the CPU, it is a faster memory, and whenever the CPU has to read an instruction, it usually refers to the cache memory. The cache memory works on the principle of the locality of the reference. Locality of the reference means if one instruction has been referenced as of now, it is very likely that the instruction near to that will be referenced in the near future. So, rather than bringing only one instruction from the main memory, we are actually bringing block of the block from the main memory, and the block contains multiple instructions, multiple nearby instructions than the current referenced one. Similarly, the cache memory also works on the principle of the temporal locality of the reference also. The temporal locality of the reference means, let us say we have a for loop wherein a variable is used to reference to that for loop. For example, there is a for loop, let us say for I equals to 0, I less than or equal to 100 and I plus plus. So, it is likely that this I will be used 100 times or 101 times in fact. So, since it is the variable which is used multiple times, and in each of the execution of the for loop the I is used, it means it is going to be used very frequently. So, if we keep this instruction in the cache, so CPU will always be referring to that I or that variable from the cache itself. So, it is very useful method of keeping those instructions in the cache memory which are executed very frequently. So, there are two types of the locality of the reference on the principle of which the cache memory is working. One is the temporal locality of the reference that we discussed just now, and another one is the spatial locality of the reference that we discussed prior to that. It means bunch of the code is brought. Let us say there are 50 instructions in our program, and the block size is let us say 10. So, we will be bringing 10 instruction from the program to the main memory. If the first instruction is executed by the CPU, it is likely that the second instruction will be read next, third instruction will be executed next, and fourth instruction will be executed next. So, since since memory reference to the main memory or reference to the main memory is costlier than the reference to the cache memory, we usually bring the bunch of the instruction to the cache memory. Whenever we are dealing with the main memory management, it is also very likely that the programs or the CPU may try to access the region of the memory which is not the part of your program. So, a kind of the protection is also needed whenever we are dealing with the any memory management technique. Now, we have discussed about the logical and the physical addresses also on the last turn. Just a quick recap of this. The CPU references an address considering that 0 is the first address of your process. It means if this is a process, let us say, and this process has multiple instructions, let us say it has 128 instructions. So, 0 is the address of the first instruction and 127 will be the instruction of the last instruction, address of the last instruction. So, CPU will always be referring to the addresses in between 0 to 127, but in physical memory when the process gets accommodated, it may be accommodated in any of the region of the memory. So, let us say this region of the memory starts with the address 10,000. Okay. So, the process, the given process will be stored from 10,000 address to 10,127. So, the range of the addresses from 10,000 to 127 is called the physical address space, and this is called the logical address space. Any address in between 0 to 127 is the logical address, and any address in between 10,000 to 10,127 is the physical address. So, physical address means the address of your instruction in the main memory, or you can say that this is physical location of your address in the main memory. However, the CPU references the logical address only, and it ranges from 0 to any high address that you have said, or the total number of instructions. Based on the logical and the physical address, we also have discussed on the last turn the memory management unit, the MMU, and MMU is responsible for the conversion of the logical address to the physical address. So, MMU is a very important component of the operating system, because every time CPU will be referring to only the logical address, and based on the different schemes that we are using in the memory management, it is the responsibility of the MMU to convert that to the physical address. Now, we also have discussed about for management of the memory, obviously, that it is very useful to keep the CPU as busy as possible. So, since we need to keep the CPU as busy as possible, we should accommodate as many processes as possible. With the time the RAM size is increased, but as of now you can see that the 8 GB RAM is very common in our personal computers or even our mobile phones. The 8 GB is sufficient enough to work with the processes that we are having, but we can only handle about 1000 processes in 8 GB. I am not telling you the exact number, it actually is just a guess that let us say 1000 processes are running in the 8 GB of memory. So, even then whenever this when even the 1000 processes are running in the main memory in the computer system, the CPU is not 100% utilized. When you will run the when you will press Alt Control then and will see the CPU utilization, it is around 20 to 30%. So, it means that most of the time the CPU is not that very busy, it is free. So, 70% of time it is free. It is because the IO operations take a lot of time. CPU utilization takes less time. So, with the formula W dash equals to W raised to the power n, you can find out how much is the IO operations or how much time the IO operation requires. As you increase the number of the processes or degree of multiprogramming in your system, the IO operation goes down, or the time for the IO operation goes down in percentage, and CPU utilization increases. But CPU utilization does not increase linearly, and with this formula you can say that if W dash is the W dash means W raised to the power n is the IO time utilization, then the CPU time utilization will be 1 minus W raised to the power n. If you take a limit, and since you want that 100% time the CPU should be utilized, you want this figure to be 1. So, that is only possible if W raised to the power n is 0. Since W is in fraction, by increasing the power its value should be decreasing. So, it is 0 or it is assumed to be 0 at infinite only. So, you can accommodate infinite number of the processes in your system. So, that is what we have discussed on the last turn. We now discuss about the contiguous allocation schemes, and the contiguous allocation scheme says that you have the main memory. In main memory there will be two regions. One is the OS region and the other one is the user process regions. The user process regions or user region, in the user region you can put as many processes as possible, but the first scheme says that you should actually store the processes in the contiguous region only. What is the meaning of the contiguous region? Let us once again draw this, and this is the OS region. Let us say my address starts from 100, the user region starts from 100 and it is up to 700. Okay, you may take it in any unit, 700 kilobyte or megabyte, whatever you like. Let us say we have a process of 150 units or 150, let us define it by 150 bytes. So, if it is 150 bytes, it has to be allocated in the contiguous regions. So, from 100 to 249 or 250 you can say, this is where the process is getting stored. So, process will get stored in the contiguous region. If another process comes, let us say that is P2 process, and it has a size let us say 160 KB. So, it should start from 250 and go up to 410. This will be stored in the contiguous regions. So, contiguous region means the entire process is stored in one region only, in the one contiguous region. It cannot be scattered, or the program or process cannot be divided into the parts and stored in various regions. We are trying that the entire process is getting stored in one region only. So, the first scheme says that we should maintain the fixed size partitions. For example, if we have the user area of 400 kilobytes, then the user area of 400 kilobyte is divided into 100 bytes, 4 chunks. You have fixed the degree of multiprogramming here. You are saying that not more than 4 processes can get accommodated here. It means the degree of multiprogramming is 4 here. So, this is one of the scheme of the contiguous allocation, where you are maintaining the equal size partitions. So, whether the process be small or large, they have to be accommodated in 100 KB space. So, if the process is of 20 KB, so that will be accommodated in here in any of these slot which is free. If the process is of 90 KB, that also be accommodated, that also will be accommodated in any of these blocks. Now, the another scheme is that we should use the variable size partition. The meaning of the variable size partition is that we should create the partition of unequal size. So, here you can see that there will be operating system region also. Let us say the operating system region lies here. Let us say we are starting from 0 here. We are just assuming that this is relative one. So, 0 is starting here. So, these are the different partitions that we have created, and these partitions are of unequal size. One is of size 100, 500, then 200, 450, 600. So, based on the observations or based on the size of the processes that we usually see, we have divided this into the various parts. Now, the degree of multiprogramming here also has been fixed to 5. So, n is equals to 5. You cannot accommodate more than 5 processes in these chunks. So, the two schemes, the one suggests that you should divide your memory into the equal size partition. The other scheme says that you should divide your memory in the unequal size partitions. Now, when we are having the contiguous memory allocations, let us say we are accommodating a process P1 here, P2 here, P3 here, P4 here, and let us say P5 is accommodated here. So, you will always like that any instruction of P1 or any reference instruction of the P1 should not to be affecting the P4 and P3. So, we should define the process boundaries. Okay, we should define the process boundaries. So, for defining the process boundary, we can say that this address or the starting address of P1 process, let us say it is 100 address, should be stored in some register, that is base, and the size of the process should also be stored somewhere. Let us say the size of the process is 470. So, size of the process is 470, but the partition is of 500 size. So, what we will say that the limit is either 470 or 500, whatever you like. Let us say we are taking limit as 470. So, P1 process or reference to the instruction of the P1 process should lie in between 100 and 470 only. This is 370, let us say. So, the base register should contain the starting address of the process or the partition, and the limit register should contain the size of the partition. Okay. So, we can say that there are two registers that we would like to take here to protect the memory regions. So, for protection of the memory regions, two registers are required here. So, we can say that this is the hardware support for the contiguous memory allocations with the fixed size partition or the variable size partition. This will be required for the both. Now, this is the diagram that will make you understand about what I said just now. A CPU is referencing the logical address. So, when the logical address is referenced, so let us say we are referring to this one, and here we are saying that, let me remove all these things, and let us say P is a process. For P process, let us say starting address is 100. So, the base address should be containing the address 100. Let us say the size of the P process is 370. So, the address where the P process will end will be 469. From 470, the 470 to 600, because this is of size 500. So, from 470 to 600 there will be no instruction. Okay. So, my limit is up to 469 only. So, what I am storing here in the base register, I am storing 100, and in the limit register I am storing 370. So, whatever instruction is referenced by the CPU, that will be lying in between 0 to 369. In case the CPU is referencing any instruction beyond 369, it means there is an error. So, we should first check if the CPU has referenced the correct instruction or not. So, CPU has referred to an instruction that should be less than the size of the process, and the size of the processes is stored in the limit register. So, if logical address means the address issued by the CPU is less than the limit register means the size of the process, then it is fine. Otherwise, we will throw the trap, which is the memory addressing error. I already have discussed about the trap on the last time. Now, if all is well, let us add the base register to this CPU address, that will give us the physical address. For example, the base address is 100. If I am referring to the first instruction means the address will be 0. So, I should add 100 to this such that I can get the first instruction at address 100. Similarly, if I am referring to 74th instruction, so meaning of the 74th instruction will be that I will add 100 to this. So, this will be giving us 174, that will be the physical address. So, physical address can be obtained by adding the value of the base or the relocation register, and then we will be referring to the main memory where my instruction lies, and I can read this instruction and give it to the CPU for the execution. So, this is what the hardware support required for the fixed size partitioning. Now, let us solve a question to have a better understanding of the fixed size partitioning schemes. Consider 5 memory partitions, 100 KB, 500, 200, 450 and 600 KB in the same order. If sequence of requests for blocks of size 212, 417, 112, 426 come in the same order, then which of the partition algorithm makes the efficient utilization of the memory? So, for efficient utilization of the memory or fitting the processes in the blocks, we have some of the schemes known as best fit, worst fit and best fit, first fit and worst fit. The best fit algorithm says that you should accommodate your process in that partition by which the minimum wastage of memory is there. For example, if I have the partitions of 100, 200 and 300 sizes and the process size is let us say 160, I can accommodate 160 size process in 200 size block also and 300 size block also. If I accommodate it in the 200 size block, the wastage will be 40. If I accommodate this in 300 size partition, then the wastage will be 140. So, I should prefer 200 size partition because the least memory, least fragmentation is there for this partition. Okay. If I accommodate the process in 200 KB or 200 size partition, there will be a 40 size wastage here. So, the best fit algorithm says that. Worst fit is just the reverse. If it is the worst fit, we should fit it in the 300 size, because there is a maximum wastage there. The first fit algorithm says that where there are various partitions, you just scan the partitions from top to bottom and find out which partition is suitable enough to accommodate your process. So, you do not have to go for the memory wastage, you do not have to think about that. If the slot or the block is sufficient enough to accommodate your process, you should go with that. So, for this question, for solving this question, let us say we have made the memory blocks like this. This is 100, 500, 200, 450 and 600. Let us say we are going with the first fit scheme. So, the first fit scheme says that, let us look at the processes and you will be able to understand the first fit. So, P1 process 212 size, I cannot accommodate in 100, I can accommodate this in 500. So, let us say we are accommodating P1 here in the first partition. So, if I accommodate P1 here, the size of the partition is 500, there will be a wastage of 388 bytes, 288 bytes, not 388. Okay, there will be wastage of 288 bytes. Then we have a P3 of 112 size. I cannot accommodate P3 in 100 size. 500 size partition has already been accommodated by P1 or has already been occupied by P1. Then 112 can fit here in 200 size. So, P2 can go here. With this, the total wastage of the memory is 88. Okay. Then you have P2 process, just scan it from top to bottom. 100 cannot accommodate 417 size, 450 can accommodate. So, let us accommodate this this is P3 process. Let us say we are taking P2 here, or this is 212, 417. Okay, we will have to change the order. So, changing the order, we will take this one first and then this. So, 212 can accommodate here. Then P2 of size 417 can only accommodate here. Okay, I am going with the first fit scheme. So, 100 cannot accommodate P2, 500 has already been occupied, 200 cannot accommodate this. Yes, P2 can be accommodated here in 450 size. Then let us take P3, this is 112. So, 112 cannot fit here. Yes, 112 can fit here. So, P3 will fit here. Then I am taking P4 of 4 to 6 size. So, 4 to 6 size process, P4 can be accommodated here with the first fit scheme. So, you can see that with the first fit scheme, all these processes have been accommodated somewhere. Okay. Now, let us look at the best fit scheme. Best fit scheme says that we should actually find out the partition which gives us the minimum fragmentation or minimum wastage. So, the 212 size process will go in the 450 size partition. Okay. P1 will go here because this is the minimum wastage, this is allowing you the minimum wastage, although it can get accommodated in 500 and 600 also, but the minimum wastage is in the 450 size. Now, let us take P2, it is 417. So, out of the available ones, P2 can be accommodated here only, because there are two partitions that can accommodate P2, one is 500 and one is 600, but the 600 size partition is too big for it, it is a best fit scheme. So, let us fit it here in 500 size. Now, P3 is 112 size. So, 112 size process will fit here in 200 size partition with the minimum wastage, although this 600 size partition can also accommodate this. Now, P4 process is of size 4 to 6. So, I have only one option of P4 fitting here in this 600 size partition. Now, let us do it with the worst fit algorithm. The worst fit algorithm says that we should fit our process which in the partition that gives us the maximum wastage of memory. So, maximum wastage of memory, let us say P1 is being taken. So, P1 will be accommodated here in 600. Okay. Then P2 417, it should go here. With P3 with 112, should go here, okay. And then P4 with 4 to 6 cannot be accommodated because we are left with only 100 and 200 size partitions, which will not be sufficient enough to accommodate the 4 to 6 process. Now, for the given question, you can say that the best fit and the first fit, both algorithms are fitting our processes well, okay, and the worst fit is not able to fit P4 process. Now, this is again the example of something which is asked of the similar manner, that consider the 6 memory partitions 200, 400, 600, 500, 300 and 250 KB, where KB refers to kilobyte. These partitions need to be allocated in for 4 processes, 357, 210, 468, 491. The best fit algorithm is used, which partition is not allocated to any process. Very simple. For solving this question, let us say we are taking the partitions. The partitions are of size first 200, second 400, third 600, fourth 500, and fifth is 300, and the sixth one is 250 size. The processes that we have to accommodate, the first one is 357 KB. So, 357 size process, let us say this is P1. So, P1 will be accommodated here, because this will give us the minimum fragmentation, and this 210 can be accommodated here. So, let us say this is P2. Then 468 should be accommodated here, let us say this is P3, and then we have 491 should get accommodated here in this partition. So, the size of the partition 200 and 300 is vacant, no processes have been allocated to these partitions. So, this is the correct option. So, out of the schemes available for best fit and first fit and the worst fit algorithm, there is another algorithm known as the next fit algorithm. Next fit algorithm, what does the next fit algorithm says? Let us say there are 6 partitions, or there are several partitions. Let us say out of these several partitions, let us say I have accommodated my process here with the first fit scheme. So, in the next go or next for the accommodation of the next process, we should not start from the first partition. In fact, we should start from the next partition that we have taken just now with the first fit scheme. So, if I number these partitions 1, 2, 3, 4, 5, if I accommodated the last process in the third partition with the first fit scheme, the next fit scheme will start searching or scanning from the fourth partition, not from the first partition. So, this is the next fit scheme. Now, you can solve several questions. For example, this one, this process, this question is saying that there are some slots which are of size 4, 8, 20 and 2K, and you have the processes, and the process execution time is also given. You just have to find out that where or when will the process of size 20K finish. So, you can solve it by yourself. So, a very quick look at the fragmentation. Whatever is the wastage of memory here, that wastage of memory is complete wastage of memory. If you are accommodating a process of 360 KB in 500 size, then 140 is the wastage, and that wastage cannot be utilized for accommodating any other process. So, this is known as the internal fragmentation. So, internal fragmentation means the wastage of memory which cannot be utilized for accommodation of the processes. So, external fragmentation we will see on the next turn with the other scheme. So, this is the reference for today's lecture, the operating system concept by Silvershire and Galvin. In the next lecture, we will see the dynamic partitioning scheme. Thank you.